Section 5.4 Logarithmic Functions. So let's look at an example. It says $2,500 is deposited into an account paying an annual rate of 6.0% compounded continuously. Calculate the balance after 5 years. So at first glance, this problem looks very similar to ones that we have done before. It's a financial model of some kind. We have a APR of 6%, and we have a compounding rate or a compounding period, but then the thing that's different is that it says compounded continuously. So what does that mean? And then ultimately we want to find the balance in the account after 5 years. So as this footnote says here, we have actually kind of looked at a very similar problem before where we calculated 5-year balances for a 6% APR account with these compounding periods, so an annual compounding period or a semi-annual, quarterly, monthly, weekly, and daily. And just to remind you, for example, the quarterly looked like this. So the amount in the account would be $2,500 times 1 plus 0.06, that's your APR, divided by 4 to the 4t, and then we would evaluate A at 5, and that would be our answer. Okay, so obviously we're using this compounding model, which is A sub 0, 1 plus APR over n to the nt. Now that's the model for when we have a discrete number of compounding periods. So n is 4, n is 365, or something like that. But what do we do with this continuously compounded statement? Well, let's talk about it. So this is an example of what we call continuous growth. And when we're talking about a continuous growth situation, in other words, interest compounded continuously, we basically have a new model, and the new model is given below. In shorthand, in short, this would just be A of t equals A sub 0 e to the APR times t. So there's something in here that you might not recognize, which is that E. What does that mean? But A sub 0 is the initial amount of money in the account. APR is the annual interest rate as usual, also known as the nominal rate. So that's another name for it. And that's expressed as a decimal value, not a percent. But what is E? Well, just to cut to the chase, E is approximately, it's a number, and it's approximately 2.71828. That's an approximation. In actuality, E is a non-terminating, non-repeating decimal value in the same way that pi is. You know, pi, we approximate pi as 3.14, and we can approximate E like as I've written there, or to any degree of accuracy that we like. Of course, that doesn't really answer the question why we're using it or where it's coming from, but that is at least tell you what it is. The other thing I'll just go ahead and mention is that E, when you're actually working with this, you do not need to type this in every time because your calculator has a button right here. So you see where it says ln. We're gonna use ln itself, but we're also going to use second ln, and that's e to whatever. So if I raise this e to the first power, just to show you, e to the first power is just e, and that's 2.71828, and then it actually repeats the 1828 another time, and then it's something else after that. But so we could say e squared, and that's this number squared, and so forth. So this is going to be very important whenever we're talking about continuously compounded growth, or decay for that matter. All right, so just to kind of get some facility with calculating, back to this model, A sub 0 is $2,500, the APR is 0.06, so our model is this, 2,500 times e to the 0.06t. This is our continuously compounded growth model for the given APR and initial value. And so then to find the function value, let me just show you. We'll type in 2,500 second e to the x 0.06 x. And I think I got a little crazy with my parentheses. I didn't really need this one. That is sufficient right there. And then we will just evaluate the model at 5. Okay. Find the effective annual yield for an account paying an annual rate of 6% compounded continuously. So we're still kind of just getting used to using this continuously compounded scenario. But this right here, the effective annual yield, that should kind of look familiar. So the effective annual yield, remember, we did this before using the, actually I'll just write it in here, the old EAY formula, okay, was EAY equals 1 plus APR over n to the n minus 1. That was the old EAY. Now when I say old, what I mean is the n times compounded EAY. But we're not in that situation anymore. Now we're in the, well, I guess we're in the new EAY, which is continuously compounded. So if you have a model that's continuously compounded and you have a stated APR, but you want to know what would be the effective rate for that APR, and it's continuously compounded, then what we're going to do, I'm going to go back to this model, we're just going to take this portion right here, this e to the APR. So EAY will be e to the APR, no variable. Just as before, we do not use the t variable for the effective annual yield. We get that value, then we subtract 1 from it, and I guess for both of these, to put them in percent form, we multiply by 100. Okay, and that's your rate. So this slide that you're looking at now just explains that in a bit more depth. And as I said, it's the investment's exponential growth rate, and there is the formula to memorize. So for the example that we just did, the EAY would be e to the 0.06. Let's actually compute it. So second e 0.06, no t, no variable, subtract 1, and multiply that by 100. And you get 6.184%. Okay, let me just, for just a brief second, address the use of this number e, and tell you a little bit about where this comes from and why we're using it. Now, I'm not going to go into a full depth mathematical explanation. I just want to give you a glimmer of why the value e is used. Okay, so if you look at that compounding formula for discrete compounding, you know, this guy right here. All right, I'm going to write something else down which is sort of similar to this, but not exactly the same, but will look very, very similar. So if you take this this expression, 1 plus 1 over n to the n and calculate its value as n gets large. So in other words, what would 1 plus 1 over 100 to the 100 be? Or what would 1 plus 1 over 1,000 to the 1,000 be? So in terms of this, what the connection is between what I'm writing down right here and this original continuous or discretely compounded financial growth model, the only different thing here is that I have some initial value and then I have an interest rate, an APR, that's put in the numerator of this fraction. Other than that, it behaves pretty much mathematically the same. So what happens to this expression as n gets large? Let me just show you by computing a few of these. So let's start off with 100. So if I do 1 plus 1 divided by 100, and then I raise that to the 100th power, I get 2.704. Now you might see where I'm going here with this. And now 100. Now let's try it for 1,000. So parentheses 1 plus 1 divided by 1,000, caret to the 1,000th place, or sorry, the 1,000th power. And this is 2.717. So this is approximately 2.71, and this one is approximately 2.7. Actually, let's go to 3 decimal places. 2.705, and this one's approximately 2.717. Now, if you imagine that this n, which is 100 and 1,000, imagine that represents compounding periods. So essentially what we're doing is we are increasing the number of compounding periods per year from 100 to 1,000. Now, if you let n get bigger and bigger and bigger, you're going to be compounding more and more and more often, and eventually you're basically going to be compounding all the time, i.e. continuously. So as n goes to infinity, we call this sort of continuously compounded. And this expression, as n gets bigger, the expression, what is it getting close to? Do you see that it's getting close to 2.718, and etc.? So this expression is approaching e. So as n goes to infinity, this is approaching e. And so our formula, as n, and there's a few little mathematical details that I'm skipping over here, but the basic idea is that as this n value gets really large, this expression approaches a sub 0 times e to the APRT. Okay, so that's just a little justification for why in the world we use this weird e value. Okay, all right. Now the thing about this is that this actually applies not only to financial models, but this also applies just to any growth model, or any continuous growth or decay model, as long as it's continuous. And you've probably seen this equation before. You've probably seen it written as well, there's a lot of ways, but a lot of times you see people write this. PERT. I probably won't use that very much, but I just want to mention that it is the same thing. Okay, so I'm going to erase that actually. All right, we'll pause here.